Hello, hello. Can you guys hear me? So I'm just calling the team names first before we begin. Team Ain, AINE Team Ain, Gunda Venkata Shanmukha. Are you here? Ha, okay. So Team Comrades K Vikas Mahender. Okay. Team K Vomik Kaushik Arnav. Okay. And Team Crispy Christopher Paul. Achha. It on? Hello. Huh? Hello. Huh? Yes. Hello. 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 Oh, fine. Yeah. Can I see? Okay. Hello. Can you guys hear me? You guys hear me? Fine. So we'll start, right? So I think, thank you for coming to the Datathon session, right? So I'll give a very brief presentation in 5 minutes. What the Datathon was about and what was the process. This will be good for the audience and for the panelists and for the participants as well. So we first tried to look at, we wanted to make sure the Datathon is kind of a one of a kind hackathon, which is not directly equivalent to Kaggle. So we sought datasets from our industry partners. We selected one task which covers multiple modalities. So we selected the document classification task. And to make sure that we do a little bit more evaluation, we also made sure that we evaluate not only on public test sets like Kaggle leaderboard, but also unseen test sets, which are testing different variations or the generalization capabilities of the systems submitted by the participants. We also evaluated participants based on submitted reports. So in comparison to Kaggle, the difference primarily is that the participant So the participants had to submit their code, the report, right? And they were filtered based on whether the code worked on a similar but differently created dataset, right? And the innovation and the research potential that we saw in the reports. So the task is like this, a very simple task. Given a document grayscale image, right? You have to classify between 16 classes. These classes can be seen letter, memo, email, file, folder, etc. Right? These we actually had a discussion with an Adobe researcher, and according to him, it was a data set of interest. That's something that might be useful for our industrial partners, right? So this dataset actually was huge. It's almost in millions. This is RVL CDIP datasets. It's a publicly available dataset, almost in million. To make sure that since BTech students participated, we wanted to make sure they can handle the training set itself. So we carefully selected 16,000 images, right, to be in the training, construct the training set. We randomly selected 900 images, non-overlapping with the training samples for the validation set. And our volunteers, especially Shomodeep Rai and Shayantan Adok from IIT Kharagpur, has carefully created the unseen test set that is coming from a different data set itself. For example, we considered a subset of tobacco 3482. Remember, this has not been even shared with the participants. In fact, I'm sure that they even did not know that this was what we finally evaluated on, right? So tobacco 3482 has 10 unique classes, and out of them, 9 were overlapping in RVL CDIP. We selected 880 images and added Gaussian noise to randomly selected half number of images, 440 of images, and 440 we just kept it untouched. So this is how a data set was created to make sure that you cannot overfit on the given training set, right? So the people who are here, they created systems who are generalizable enough, which is fit in itself, right? So this is the primary process. So we opened, so this was almost a month-long process. So we started on sometime in August. We had on 10th August or so, we had an AMA session sometimes between August and September. And in the whole time from 8 to 10, they had a 1 to 2 month long period of coding and going through this competition, right? And they had to submit the code and a short report about their procedure. Once they had that, in 1 month, we announced the top 5 teams, which we have called for presentation today. And based on the presentation, based on their innovative skills, and we will announce the winner today itself. So just to make sure that you understand the statistics. So this time we will say that it's a very successful set of people. The fact that this was a researchy datathon, right? We are clear. So 102 teams participated in Kaggle with 192 members. They had 670 Kaggle entries, right? So you will see in leaderboard there are 670 entries. And among these 102 teams, 34 teams submitted the code, the full code and the report. And among those teams, the top 5 teams are here, right? Team Ain, Gunda Venkata Sharmukha Sainath, Team Comrades, Team Cake, Team Crispy, and Team Noobs. And all of them today will present for 10 minutes or so. They will have 2-3 minutes. The audience and the panelists will have 2-3 minutes for questions. Based on that, we'll be judging the final things. I would also like to welcome our esteemed panelists, Monojit Chaudhary, who have already listened to his talk, Principal Applied and Data Scientist in Microsoft Turing, Ashish Kulkarni, who is Associate Research Director in Rakuten, and Rishabh Iyer, who is Assistant Professor in UT Dallas. We are very, very happy that they have agreed to judge as a panelist. Thank you. And just to introduce us, this was the Datathon organizers, Vidisha, myself, Jayesh, and Sandipan. We are from various universities and organizations, right? And but we couldn't have completed this without our dedicated volunteers primarily from IIT Kharagpur. They had to go through codes, reports, they had to actually install things, and they had to also communicate with the teams to make sure the code run, which is actually a huge, huge feat. I don't think Kaggle has done something like this before. Okay, so I think it's already 10 minutes almost. So I'll hand it over to the first team. I think the first team is probably Team Ain, right? First team is Team Ain, yeah. So 10 minutes and then. Okay. No. You are the first.
Yeah, order. You can use that podium as well. Just switch that. That's what this is right.
Hello, am I audible? Yeah. Good evening, everyone. This is Vikas, and we have Mukund here with us, and we're here to present our solution for the Datathon submission. So essentially, okay, is it? Okay. So this is Vikas, and we have Mukund here with us. So we are here to present our solution for the Datathon submission. So essentially, we are looking at a task, which is a visual document understanding. So given an input image, which represents a document, which is a scanned image, we are looking forward to classify it into one among several classes. And for the given sample here, it's going to be a news article. This task is not so easy. It is challenging because most of the documents tend to have a complex structure. And also these documents have diverse templates and layouts. And similar classes may have diverse templates and layouts, and that is why it's challenging. One another thing is that a standardized approach in this task is to basically use either image-only methods or use a text-only representation. So if you're using only an image-only model, so what happens is the performance is often determined by the quality of the representation. Like, let's say you have a blurry image, then the performance degrades. And moreover, like, let's say for the sample shown here, we have a scientific publication and a news article. So both of these, though belonging to separate classes, they have little to no visual difference between them. And an image-only model may find it difficult to distinguish between these two things. Similarly, in the case of a text-only model, the performance is often determined by the quality of the text generated by an OCR engine. And if you're using only text, we often neglect the information pertaining to the structure or layout of the document, which is highly crucial in these kinds of tasks. So to this end, we are proposing a multi-model technique, which will basically try to take the best of both worlds, both image and text. But one inherent challenge in this space is to, like, how can we fuse effectively two unrelated modalities? Like, for example, in image and text, which are totally unrelated, how can we fuse them effectively in order to have a good classification pipeline? So to this end, we propose a document image text transformer, DIDT. So the flowchart shown here represents our stage-by-stage pipeline. So basically, given a document image, visually rich document, we have the feature extraction stage, which is the first stage, to generate image and text tokens. And we have our multi-modal feature interaction stage. So here from the okay, so in the feature extraction stage, we generate latent information or feature representations from the document. And in the multi-modal feature interaction stage, we take the visual feature representations of the image and text, and then we fuse together using our novel mechanism. In the feature extraction stage, we use an image encoder to generate image tokens. And similarly, for the text encoder, we use an OCR engine to first generate the raw text from the document and also the bounding boxes of each and every word present in the document. We then pass the text onto a text encoder to generate text tokens. Before going on to like deciding like what is the motivation for our design choices, let us show we have shown an illustration here. So let's say for the given document, we have the image and text tokens for each and every patch and so on, and each and every word as well. So apart from these information like image tokens and text tokens, we also consider the patch centers. Like for every patch of an image, we see like where the image is present. And also, we also take the center of the bounding boxes for each and every word. So what happens here is that the image and text tokens represent the semantic context of the document, and the patch centers for the image and text boxes determine like the spatial layout of the document, which will give you a sense of like what is the structure of the document essentially.
Towards this end, we propose an image text transformer, which is a modification on top of the standard attention operation. We call this layout augmented attention. So our idea is quite simple. We take the existing attention operation where we basically compute the queries from the image tokens and derive the keys and values from the text tokens. And basically the relationship between them would define the semantic relations between the image and the text components. Additionally, we also derive pairwise distances between the patch centers and the box centers. And this basically represents the spatial layout relationships. Now, instead of doing a naive aggregation scheme between these two relationships, we add a gating parameter, which automatically learns to regulate how much of information should it focus on the position versus the content information. Formally, that is described in that equation, where we basically have a learnable parameter called as a gate, which will decide how much of information it needs to select from each. So this is our training data set. This is already discussed. We'll skip this slide. These are our experimental settings. Most notably, our feature extraction pipeline uses a pre-trained image encoder, which is a VIT. and our pre-trained text encoder is a BERT. Since we have very limited training data, we use a strategy called as auto-augment. It's basically a learnable augmentation strategy on the images, which identifies the best policy. And we are optimized both cross entropy and an additional loss called as cosine loss. Now, why cosine loss? We say that cosine loss improves data efficiency. The reason is quite simple. Cross entropy, to reach optimum, the feature value of the true class must take maximum value or infinity. So that leads to very confident predictions, or that can lead to overfitting. But however, the other end, cosine loss is more bounded from 0 to 2. And also it has an inherent normalization, which leads to hyperparameter free regularization. There are additional benefits as well. For example, it has a robust initialization. That is, irrespective of the initialization, it will always reach the descent faster than cross entropy. But mainly we focus on the data and to avoid overfitting. So we first consider, before talking about our method, we consider some baselines. Our first baseline is an image-only unimodel method, where we have an encoder followed by a single layer classifier. The encoder could be a convolutional model, or it could be a transformer-based model. And these are our results. And we can see that, so what you see as DIT is basically a document image transformer, and image transformer trained on document images. We see that even models pre-trained on document images fail due to the limited training data size given to us. We also consider multimodal baselines to compare our specific strategy. We consider a strategy where we extract both features from the images and features from the text, and basically aggregate it using a simple addition, concatenation, or a max pool strategy. And we see that concatenation strategy works best. If we conclude that multimodal methods outperform image only, that is unimodal methods, by at least 4%. Then we talk about our method. We can see that our method further improves the performance on top of the multimodal methods by at least 3%. In fact, this performance can even improve if you use even better strategy, better encoders. For example, if you use the layout LM, which is a BERT model trained on images, on text from documents, it further improves performance by at least 2%. We then visualize or try to infer what sort of what the model learns. We first try to find the correspondences within the images itself. For example, for this particular scientific report, these are basically the attention matrices extracted, or basically the relationships between the patches in the image. And we can see that each head sort of focus on different sort of information. For example, the leftmost focus on the overall layout, that is, there's an abstract followed by 2 paragraphs. The second head focus on the fact that this is split by a 2 column, and the last one focuses on the title. We also visualize the image text correspondences, more specific, and we see that beyond just the layout information, that is positionally where the text is, it also focuses on trying to abstract out stuff. For example, if you see that particular column with full of numbers, the model automatically discards all those numbers and says that it needs to correlate to something like a dollar symbol. So dollar symbol would basically indicate price, and it would have more meaning than just random numbers to a text model. And similarly, you can see the date, for example, December 31st, 1977. The exact date, 31st, 1977, by numbers, numerically, does not make any sense. So the model rather focuses on the month December more. Our conclusion is that we've basically proposed a network called DITT for multimodal visual document understanding. And we have proposed an augmented version of the attention mechanism, where we include both spatial layout information. We also leverage a regularizing loss function based on cosine similarity to improve data efficiency. And we see that our method outperforms several unimodal and multimodal methods. Thank you. Yeah.
Did you do any evaluation across different classes? Like, what was the performance across different classes?
I don't have those numbers. No, I don't have those numbers.
But any insights?
I wasn't able to find anything in particular, or that it stands out, but no, I don't remember that particular class-wise performance. I don't remember. Okay. There's one thing maybe which we can highlight is that, which I want to maybe point out, is that this performance could further improve if we use better encoders, like more VIT is trained on images, which is like just classes of dogs, cats, and so on. So if we use the pre-trained encoder, like for example, DIT trained on the RV clip dataset itself, we could further improve this performance. that is why we see that performance improvement when we replace from BERT to layout LM. But the reason why we didn't do that here is because the competition constrains us from using the full data set of the RVCL, the full data set. So that's why, but yeah, that's one point which I want to mention.
Hello. Yeah, I don't know. This might be also a question for the organizers. So was additional data or tasks allowed? Okay, because the question I had was, could you think of using the same pre-trained models, but also train with additional tasks on the same data?
Yeah.
And if they could have improved the accuracies more?
Yes. Yeah, I think like if we had a pre-training task which directly maybe predicts stuff from the document itself, like the text in between, like if we did an MLM with the document text itself, it could perhaps improve. But yeah, but the competition said that we are not allowed to use any sort of additional, like a model trained on the data of that particular data set. Okay. But given the data set size, I think the data set given to us only 16,000. I'm not sure if MLM will work really well with such small text corpus. So not sure.
Kind of related to Ashish's question here. Did you do an analysis of where the model makes mistakes? Are they harder examples? Are they specific classes?
Like I said earlier, like there was two classes. One is the resume. Sorry. Yeah. So the scientific publication and the news article. So even though we are able to comprehend that these are two separate classes, for the image models, these are basically this thing. And our model also had a lower performance impact on these kinds of similar classes. So that is one thing we had. Other than that, we haven't like one sir pointed out, we didn't actually do a class-wise thingy. So I think these are some limitations where we could have thought about further.
Good evening, everyone. It's Team Cake. I'm Hami Kaushik. We have Arnav and Kinshuk with us. And today we are going to be presenting classification via positional test for the document classification task at IndoML Datathon 2022. Let's get started. So before moving to the motivations and the solution, let's actually talk about the challenges we actually face in this particular task. First of those challenges was overlapping or ambiguous classes, right? This challenge is as follows, that when we used to look at two of the samples, some of the samples which are belonging to different classes, they have an overlap between them, right? They have an overlap of characteristics between them. If you are actually looking at these samples, the left one is actually a letter and the right one is actually a memo, but they actually have an overlap of the characteristics. So it actually makes this task a bit difficult to actually classify. The second challenge that we actually seen is that intra-class variability, right? Within the same class itself also, if we actually have a look at some of the samples, they have a lot of variability, right? If we actually look at have a look at the sample, which is actually on the left and on the right, they have a lot of variability in terms of density, right? So on the left, the sample is actually having a lesser dense content, and on the right, the sample is actually having a lot of content. So it actually also makes the classification on the base of perceptibility very difficult. Now, the third challenge we actually face while doing the classification on the basis of images is that when you used to resize the documents itself, right? When you used to resize on a downscale sample, can you actually read that? I think that it's actually hard to grasp the content of these particular document samples, but still they have the memo class, but it's hard for me to actually classify the documents on the memo. And that was the challenge we actually faced by classifying on the basis of images in our settings. So let's go for the motivation towards the solution. We actually tried to find an inspiration that how human would classify the documents, right? And we also wanted to find a particular solution that is actually easy to understand and easy to implement also. So that's according to Occam's razor. And how human would actually classify the documents. When you actually have a look at a particular document, you will look at the text, right? You will actually keep in mind the particular text. And so we will use the text for the classification purpose. And and also you used to consider the position of the particular text, right? Where it is actually lying in the particular document. So that was also a motivation for us, that what we will actually include in our file and classification model. So as we discussed in the previous slide, right, that the slide which was actually referring to the downscale or rescale sample of the images, then the problem was that it was actually removing, or it was actually degrading the degrading the quality of that image. So why not to actually supply the whole image to the document, to the model itself, right? Why not to actually use the whole image? So these are the hardware constraints which we actually face while actually evaluating or calculating that how much memory does it takes to actually classify on the basis of whole size images. So the images were of size around 762 cross 1000 for this particular classification task. And if we actually consider the maximum parameter layer of ResNet 50 model, then it is actually having the parameter of say 2.3 millions, and it is actually having an input shape of this 24 cross 32 cross 512. And if we actually consider the size of one parameter to be stored in the memory, then if we actually consider the floating point values, then it will take 4 bytes, and the total memory under consideration for one image classification will be around 3.3 terabytes. And that's actually a huge amount of memory. And I don't think I can actually get this much amount of memory. And this was for one image to be used in the batch size. If you use a lot of images, then it will be really a lot more harder. So this is actually infeasible. So now, what if we actually use the text instead of focusing on images here? So we actually extracted the text from the images like this. So you can already see that while looking at the highlighted text there, like the material requisition, text, unit cost, total cost, shop requisition, you already can get the idea or the gist that this might belong to the invoice, right? So that's actually the basic idea or motivation behind our solution, and we will be using this. And how to actually extract the text. There are a lot of solutions available out there. So we use the easy OCR. And why we use this? Because it implements the CTC, that is connectionist temporal classification. And in this particular technique, it used to slide the window along the image one by one, and then it will actually generate the predictions on the basis of those slides. And we will actually get the multiple times prediction for the same character. And then it used to filter out all this prediction to actually align the prediction to the label itself. So that is what it is doing behind the scenes. So our primary architecture was something like this, that we have the documents, and then we are actually passing the raw text to the BERT for sequence classification, and we were actually generating the output probabilities. That's a simple architecture we were considering in start, and it was actually producing nice results, but not very nice to be used in the real scenario. What happened? Okay, so what if we also use the position information also? Like if you see in these particular examples, if you actually try to visualize with your blind eyes, that there's a particular document and you have say from, to, and subject information on the top left corner of the particular document, that you can already get the idea that this might be a letter, right? So we will use the position information in this particular case, and that was we are actually implementing. So these are our motivations. We are using the textual characteristics. We are fusing the position information along with the textual characteristics for the classification. And firstly, we are using the course location and then the find location for the document classification task. So this is our updated architecture. Firstly, we have this particular document in the start. We are applying the OCR. Then we are actually getting the textual information and the position information. The output of easy OCR is something like this, that we are getting the text, and then we are getting the bounding box of the text, and then we are also getting the confidence interval, that with how much confidence it is actually predicting the text. The values which are actually predicted with the lower confidence are actually can be a noise, so they are actually removed out. And then these two information are actually fused together, and then we are actually passing it to the BERT tokenizer, and the tokenized or embedded value are passed to the BERT for the sequence classification. And now we actually generating the final values. So this is a particular confusion matrix of the results which we have got, and the results look nice. And we also try to explain our results using the SHAP, that is Shapley additive values, Shapley additive explanations. So this is actually showing us the SHAP values for a particular sample. Here you can see that the class is actually memo, and we are actually having the highlight over the samples, over the words of say date and up and other information, which might be really crucial for a memo, because we actually used to see that we used to find the term date in the memos itself, which we actually consider manually. Now, these are the results which we actually found after whole of the task. Firstly, we actually tried with the CNN over 4K samples. Then we got accuracy around 50. Then we also tried for this with the same CNN, but with lesser number of epochs. And we actually now given the whole training data set itself. Then we got a bit of high accuracy. Then we tried transfer learning with MobileNet V2. Then we got even high accuracy of say around 68%. And then we actually tried with text-based bird classification model. Then we got an accuracy of say around 72. And then we actually trained with the text and the position information on the bird classification model, and we got the accuracy around 74. These are the results we got. And while comparing the statistics over epochs versus accuracy graph, then these are the graphs for the MobileNet V2 of the image-based classification. We can already see a trend which is actually lower in comparison to the other approaches. And the position information along with the text of the bird-based classification already performing really the best among all these three. So the future prospects among these can be that we can actually improve the dataset by using some super resolution technique, like we can use GAN to actually generate the dataset itself, because we have seen that some of the images were actually blurred out, and we need to actually find the images itself to actually classify them manually also. So we can use some GAN-like technique for that. And also we can work upon the handwritten documents, because there is some handwritten content in the document which can't be actually captured really well by the easy OCR or the tools like that. So we will work on them, and we can improve the processing speed of this technique to be used in the real-time scenario. And the fourth approach is something like this, that we will actually train a particular model, given the label and the text, it will actually generate the document for us, and we will reverse this process with the decoder architecture to be able to classify these documents in a better manner. So these are the references. Thank you so much. You can actually reach us at these email IDs. This was for our presentation.
I have a clarification question. So you first apply the OCR to get the text. Then you also get the position for each of the words. Now, is it like conditioned on the words that were identified by the OCR?
Yes. It is actually conditional on that.
And how do you get that? Like, I didn't catch quite like how do you get the positions?
The easy OCR tool is already giving us both of the information, the textual as well as the position information.
Okay.
And then we need to actually fuse those all together. And then it's upon us how we actually used to fuse them. And then they are actually passed for the embedding processes.
Yeah. So my question is then, how do you fuse them as in like what you are getting position vectors and concatenating the vectors?
Yes, sir.
Or
We actually kind of say getting bounding boxes for each of the stacks, and then we actually dividing our whole page into sections to actually capture the abstract layout of the format of the particular section. And then we actually we are actually keeping one token for each section, and then we are actually associating that particular token with the text. And then we are supplying this all information for the embedding processes further to be able to classify for the classification later on. So that every text is actually associated with one particular position in the format itself. So we can actually get the abstraction of the format.
Hi. So in your challenges, you mentioned about your, certain blurry images. So how was the performance of OCR on those sort of documents?
Yes, OCR was actually performing not very well for those blurry images, because this OCR actually can't actually read the one which are really blurred out. Means it actually can read which are actually readable by the human level, but those which we can't read can't be actually captured by the OCR also. So there needs to be done some work like that technique which I actually mentioned, like super pixelization or recreating back using the GAN architecture.
Okay. So did you see any the layout information helping in these
Yes,
in these
really,
cases? Or
really.
like, what was
We
was
got
the observation?
really say significant improvement of say 2 to 4% in multiple training when we actually apply train with different weight initialize. We actually seen a significant improvement by including the position information itself. Earlier it was actually performing less, but when we actually supply the position information, it was actually performing better in previous contexts.
Thanks.
Thank you so much, everyone.
Yeah, the question that you asked about the regions, when we talked about up, down, left, right. Yeah, the image here, these colors are basically showing us the 4 regions that we used. So the red is equivalent to up, blue is equivalent to down, green for left, yellow for right. So this data was taken into and appended in an array, and the whole processing was done that way. Okay, thank you.
Is it the one on again to my hands? Okay, so is it updated one? Yeah. Okay. So just one thing is that don't walk around plants, right? Because make sure that so that is what.
So hi everyone, I'm Shanmukh Sanad, final year undergrad from Electronics Department, IIT Kharagpur. And this is the title of our presentation is Efficient OCR-ST, a multimodal document classifier. Coming to data analysis, the main task is to classify the images into 16 different document types. And this classification is mainly done on based on the content or text present in the documents. So first I extracted the text using PyTesseract OCR or Google Tesseract engine. And the left image shows the word cloud or the word frequency of all the tokens that are present in overall extracted text. You can see majority of the tokens are like meaningful, and the right image shows the sentence length or token length distribution across all the training data. And it is peaking over 200. That means the majority of the images are having around 200 tokens, which means that almost many images have considerable information from the text. Building more on the data analysis, this is one of the example from the class resume, and corresponding OCR extracted text is shown on the right. You can see OCR is almost extracting complete text that is present in the resume class. So there are many such examples where the text extracted has more information than the image alone. So in general, for image classification task, we'll have an image encoder followed by a classification layer. Here you can see text has more information than images for many of the classes. So having a textual branch along with the visual branch can be helpful. And based on that, this is the proposed methodology. There are mainly 2 branches. One is top visual branch and the bottom one is textual branch. In visual branch, first we will pre-process the image, and we will resize the image based on the experiment, and then we'll apply augmentation sequentially. And finally, normalize the pixel values. And for image encoder, we selected two encoders from one from CNN family, that is efficient net, other from the vision transformer family, that is Swin transformer. And passing the pre-processed image, we'll get an embeddings. And coming to textual branch, we'll extract the text using PyTesseract. And then text pre-processing is having these mainly 4 steps: stop out symbol, lower casing, and lemmatization. And when I observed the extracted text, there are many samples where there are spelling mistakes of the extracted text. So I used existing Python library autocorrect to perform the spelling correction. And I used the sentence pre-trained sentence transformer to convert the pre-processed text to text embeddings. And after extracting embeddings from 2 branches, I concatenated them and have a fully connected layer followed by a classification layer. And this textual branch is completely non-trainable, considering the training size that is given only 16,000, and that is not enough for the text encoder, and I don't have the enough computation power. And I trained on Kaggle GPU using PyTorch. Coming to results, so these are the results of best performing model on training data. I have shown the training data results because we don't have the ground truth labels for test data. For almost all the classes, the misclassifications are uniform, but there are 2 main classes, form and presentation. For example, form has more misclassifications with respect to invoice, and presentation has more misclassification with respect to scientific report. Form and invoice, in general, the structure looks like there will be 2 columns, and the first column has some key and corresponding values. Those form and invoice have the similar structure, so the model may be confusing because of the similar structure. And this is the classification report for the same experiment. It shows all the metrics with respect to each class, and overall form, scientific report, and presentation have the least performance out of all the classes. Coming to qualitative analysis, this is like interpretability of the results. First, I extracted TSNE embeddings from both the branches, and this is the TSNE clustering of visual embeddings and textual embeddings. As the visual branch is completely trainable, there is clear clustering seen between 16 classes. But for textual, coming to textual branch, even though the textual branch is frozen, there is slight clustering that can be seen for specification class and questionnaire class. This is the GradCam for the image encoders, that is Swin transformer. These are the 3 examples. First one is label folder, where it is for class file folder, where it is focusing on the black part. And for email, it is focusing on the headings that are from, sent to, and the subject. And for news article, it is focusing on heading and some of the text. So these are the places where we generally focus when you are asked to classify. And this is the ablation study or the overall experiments. The green one shows the leaderboard performance. If you see that, compare the 12th, the 12th row and the second row. That second row is similar to 12th row, but without text encoder. There is a 4% improvement seen with having the textual branch. And the last row shows the performance with Swin transformer that I experimented after the completion of Datathon. And Swin transformer outperformed the efficient net even with the lower resolution. And I used the 5-fold cross-validation training. And coming to challenges, even though majority of the images have informative extracted text from OCR, there are some images where the extracted text is not meaningful. Here in this case, the image is like vertically flipped. That's why the extracted text is not at all useful. And these are some of the other classes, and the corresponding top 10 frequent words are shown. See, for example, handwritten class have those top 10 frequent words which are not at all informative or meaningful. And similar trend is seen in file folder and budget. So coming to future work, focusing on visual branch, we can train the swing transformer at higher resolution and more number of training steps. In general, for vision transformer, we'll convert the image into patches and we'll pass the patches to transformer architecture. Instead of directly passing the patches, we can have a CNN head, say ResNet, and encode the information using the ResNet and pass the encoded information to transformer. And coming to textual branch, we can make the textual branch trainable. And focusing on training procedure, instead of taking up predictions only from the concatenated embeddings, we can take predictions separately and calculate the loss and add it to the original loss using some hyperparameters. And also, we can have contrast loss between text and image embeddings. And I'm not sure the second experiment will help because both the text and image embeddings are from different, they are different representations. So bringing them closer may work or may not work. And these are the references. That's
So what do you mean by the text part is not trainable? Do you mean that you didn't train it, or there's some technical challenges because of which you can't?
so
train it?
the GPU of Kaggle is only 16 GB and Swin transformer itself is occupying all the GPU. So I couldn't train the text encoder, and even the maximum training time is 9 hours for Kaggle GPU. That means I cannot train for more epochs. So I completely froze the training textual part.
Okay, so in your ablation study, did you try? I didn't see text only setting. So yeah, just text encoder and.
Okay. For text only setting, I don't have results here, but yesterday I rechecked that. With text only, I got 62% lead F1 score, and complete with only image I have 83, and having both I have 87.
Okay. And you mentioned about class confusion.
Yes.
So any thoughts on how you could sort of improve this going forward?
Currently, I don't have any idea on that.
All right, thanks.
Okay, so I have one more question. So you said that low resolution swing transformer is doing better than efficient net, right? So do you know why? What is the reason? Like, have you tried to find out? With 224 resolution, I saw. So that lost information, why doesn't it matter?
I mean, in general, for even on ImageNet, Swin transformer is performing well. Currently, I have that understanding. Maybe that the text encode is also transformer, and Swin transformer is also transformer, where both kind of work on the patches of text or patches of images. So I think that is helping.
Good evening, all. Today I'm here to present my research for Datathon titled Neighbor Document Transformers. First of all, I would like to thank the organizer and all the sponsors for providing me with this platform and opportunity. So I'll give a bit about my background. So mainly my area of experience is in NLP, particularly in optimization of transformers. So when I first came across this problem, I tried to approach it from a transformer point of view. So that my solution is also based on transformers, so which I'll come to later on. This thing to change the slide. Okay. You can stand far. It will work. So yeah, I'm Christopher Paul. I'm an algorithms and machine learning enthusiast and also a first year CSE student here at IIT Gandhinagar. So first I'll go over the challenges. So like the previous teams mentioned, there was a lot of challenges regarding the data, especially the similarity in few of the classes. So yeah, so I'm not going over those like the ones which the other teams had mentioned. So I'll go over the challenges which I faced. So when I try to approach it from a transformer point of view, so the first thing is like the results which we have currently for the state-of-the-art performance, especially in the RVL CDIP data set, the smaller models perform worse compared to the transformer-based models for those particular tasks. And in my case, when I wanted to train a transformer-based model for this particular problem, I also had the constraint of computational resources. So I'll next go over the motivation for my particular solution. So first of all, with the recent breakthroughs in NLP, so there have actually been many attempts to adapt some of its techniques. So that is why we see the use of transformers in image tasks in recent times. And the one which I'll focus on is the nearest neighbor language model paper, which was released in 2020, which described a method to improve the currently existing language models with a simple modification in order to increase its performance without any additional training data. So next I'll go over my particular solution. So my solution, which is a KNN DIT. So this is basically an augmentation of the document image transformer, which was released by, so Microsoft Research had released a self-supervised pre-training of DIT, and they had released a model which was pre-trained on the RVL CDIP dataset and on the unlabeled images of the RVL CDIP dataset. So what my solution does is it takes a document image transformer and augments the last layer. So instead of having a linear classification layer, I'm using a nearest neighbor retrieval mechanism at the end. So this requires no additional training. So this is done with a single pass over the data set. So what I'm doing is I go over the data set, I take the image, I compute its embedding, using the document image transformer, and then I store these in a data store. So I store them as key value pairs as the image and its embedding. And using a technique called phase, which basically stands for Facebook AI, is for similarity search. So that is basically their optimized tool for querying for k nearest neighbors. And at inference, the data store is queried with a vector representation of whatever is a query image So the query image is passed through the DIT again, and the vector representation is taken, and it's and the data store is queried using it to retrieve its k nearest neighbors, and the majority label which is appearing from those k nearest neighbors is taken as the predicted label. So here is a diagram which represents exactly what I went through. So if you look at it, I have training images, I have classes, and then I also compute the representations, vector representations for each of those images. And whenever I get a test image, I compute its vector representation, and then I check in the data store and I calculate the distances to all the I calculate its distances to get the k nearest neighbors from the data store, and from those nearest k neighbors, I take the label which appears the majority, and that is my prediction label. So next I'll go over what was the innovation that this approach brings. So the main point of having this feature is that it allows transformers to memorize. So right now what happens is transformers are implicitly memorizing these factual information in the model weights, in their weights. So what this approach allows is we are able to separate that information and keep the factual information aside in a data store and just use the transformer for visual understanding, visual document understanding. So that is what I've tried to do in this solution. So this approach allows the images to be memorized explicitly rather than implicitly, and thereby allowing the model to become more robust and with no need of any additional training data. So as you can see in the figure, KNN DIT, which was so it was actually pre-trained on unlabeled images by Microsoft Research on 400,000 images of that data set. And then from that data set, so after that, I created a data store. So in my data store, I tried using different sizes of images in my data store to see how the performance improved. And if you look at the graph, you'll see that as I increased the size of the data store, and when I went till 105,000, which was just 26% of the whole training data for the transformer, it actually outperformed the DIT, which was trained on the whole 400,000 images. So this actually shows how a small change in the final layer of the transformer made a huge impact in its performance. So now I'll conclude. So the results clearly suggest that learning similarity functions between images may be easier than classifying the images using linear neural networks. So that is one point which I went through. So now we could also go over and we could check whether the model improves with further increase in the data store size. Because if you look at the graph, it kept increasing and it had not plateaued yet. So maybe the model performance can increase if we keep increasing the data store size. So future work could also explore whether this method enhances the performance of other image-based transformers. So whether this method can actually be used for other image tasks. So that. With this, I would like to conclude my presentation. Thank you all for listening.
So I had two questions. One is that with this KNN approach, what is the inference time memory requirement? So like how much do you need to store at inference time?
Yeah, so there is a computational overhead attached with this method. And It was, I don't remember the exact time, but it was actually negligible because the technique which I had used the face library, so which was really efficient in extracting the k nearest neighbors.
Okay, but do you need to, there's also a memory requirement, right? So you'll have to store, I mean, with the model, you'll have to store store like a dictionary of.
Oh, yes, yes.
instances.
So there is the question of also storing the data store. So I'm trying to justify the use of extra memory and use of extra disk space for the improvement in accuracy of the transformer model.
Thank you.
What was the choice of K?
Yeah, sorry, I didn't mention that. Okay, and in order to find the value of K, I ran it on the validation data set. Right, I tried to optimize it on the validation data set. The value I got was 15. 15.
1.5?
Yeah,
Right.
1.5.
And did you compute the confusion matrix? Like what classes were more confused?
Yes, I had, but I didn't include it in this
And that's okay.
presentation. So.
But any insights, like anything interesting you noticed?
Yeah, there were a few classes like the previous teams I had mentioned. Actually, the scientific publication and newspaper had a few overlapping, so that was a bit difficult for the model to classify. And also the letter and memo classes were a bit difficult to classify. So,
Letter and memo.
letter and memo.
Okay. And do you think it can be further improved with the help of OCR? So you can also use the text data?
I think, yeah, if we integrate the OCR text data along with, yeah, maybe the performance can be improved. But then currently the state-of-the-art approaches which I saw for this particular problem were relying just on a transformer-based approach over the whole image instead of a multimodal approach. So that is why I went with this, and I tried to bring an innovation in the an existing transformer. So that was my attempt.
Thank you.
Hello, 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 hello. Okay, so I think that last team, both of them have fallen sick, and they are hospitalized. It seems in IIT Gandhinagar. So we'll share the presentation with the panelists. So based on the presentation, if they want to score them, that is definitely their decision. So we'll conclude the Datathon session here while the panelists take their final choice of first, second, third. And I would really like to, congratulate for your impressive presentations, given your first year, second year, third year BTechs, right? And doing this amazing sort of work, right? With some challenges, that's really impressive. Really impressive work. I wouldn't have done that, I'm sure, right? And we'll announce the first, second, third, the top 3 winners during the banquet, just after this. Okay, thank you guys. Thanks. Banquet is at 7 p.m. Yeah. Thank you. So banquet, I hope that it's in the guest house actually.